On the second page of problems in this lecture on finite combinatorics and counting, I have lots of problems about the cards. Okay, so let's go through these problems. The first question is, how many different 5-card hands there are with one pair of a kind? Okay, now this is really not that hard to answer, but this is what you need to do. You need to find out 4 different choices. The first is going to be a pair of a kind. But once you're done with a pair, you need to get a third card, you need to get a fourth card, and you need to get a fifth card. So there's 4 different things you need to do here. You need to make choices for a pair of a kind, for a third card, for 4 card, and for that's a 5-card hand. Okay? So your first choice is the pair. How do you get a pair? Well, you need to select the denomination that you're gonna have. Either it's gonna be a pair of aces, or it's gonna be a pair of queens, or it's gonna be a pair of kings, or it's gonna be a pair of jacks, or something else. You have 13 options for that. So I'm using multiplication principle here. Now you have to select 2. So let's say you want to have aces. You have to select 2 aces. You're not done yet with selecting a pair. You have 4 aces to choose from. You need to select 2. In how many ways you can select 2 aces out of the set of 4? Okay? You can even count that. Ace of clubs, ace of spades, ace of clubs, ace of diamonds, ace of clubs, ace of hearts. 3 choices for ace of clubs in it. Then you have ace of spade, ace of diamonds, ace of spade, ace of hearts. So we already have ace of spade and ace of clubs. So there's now a total of 5. And finally have the 2 red, ace of clubs and ace of diamonds. That's it. 6, right? It's difficult to follow. So it's easy to answer here. In how many ways you're selecting 2 out of the set of 4? 2 different. You cannot repeat the same ace. Out of the set of 4. And the order doesn't matter. Ace of clubs, ace of diamonds is the same ace of diamonds and ace of clubs. So this is a combination. Combination 4 chooses 2. So this is the number of different pairs pair of a kind you can get. 13 times, this number by the way is 6. Of course you can use the formula, or you can use your calculator to calculate, but one way or the other this number 4 chooses 2, combinations is 6. So you have a number here is 78. If I'm not mistaken, 6 times 13. Okay, now done. Now you need a third card. You have the remaining 48 card for the third card. Why? Because if you have one pair of a kind you choose aces, you can't have any ace anymore. So you have to throw aces out. So you have 4 less. That's 48. The same way you can get a fourth card. You have now 44 choices for the fourth card. Why 44? Because if this is a pair of aces here, one of the choices is a pair of aces, the third card could be, I don't know, queen. You can have neither aces nor queens again, so you would have 44, 8 less than 52, and by the same token the fifth card will be 40 possibilities, 40 options for the fifth card. Okay, so you can say, okay, I'm done here. If I calculate this, is going to be easy. I can multiply these numbers, and I have 78 times 48 times 44 times 40, and I got the 6,589,440 different 5-card hands when I have one pair of a kind. And then you immediately notice this something is wrong, because the total number of 5-card hands you have is 598,960, and all of a sudden you have a 6 million possibilities with pair of a kind. So something is wrong here. Okay, what is wrong here is the story here. Okay, let's say that you have chosen aces, so you have a pair of aces. Now you could have here 2 of spades, so you got, for the third card you can't have any more 2s, so let's say you have now 3 of hearts for the fourth card, and you have, I don't know, 7 of diamonds for the fifth card, and so I don't know, you have a pair of aces here, like a pair of kings, a pair of spades and pair of clubs, right? Now the problem is here that I could have this third of hearts, 2 of spades, and 7 of diamonds, and it's still the same hand. Okay, now what I need to consider is that the order will not matter here in the third, fourth, and fifth card. So this as a third, fourth, and fifth card is the same as this, just different order. So the question is how many ways you can reorder these guys so that you actually have the same set of third, fourth, and fifth card. And you can reorder 3 cards in 6 different ways. 3 chooses 3 permutations. So you need to divide this number, or number of ways to get third, fourth, and fifth card, with 6, because each one of those, like 2 of spades, 3 of hearts, and 7 of diamonds, is actually 6 times here in this 48 times 42 times 40. 6. Okay, so now I know. I have, this is 6 times too big. 6 times. So if I divide with 6, I have my answer. Okay, now 1,098,240 different ways. Okay. I could have done this differently. Okay. And that's described here in this answer here. So instead of having a third card, one of the 48, the fourth card, one of the 44, the fifth card, one of 40, and then divide with 6 because the order doesn't matter, I could have done this third, fourth, and fifth card differently. And that's going to be, I'm going to select here 3 different denominations. So since I already have a pair of a kind, I have 12 remaining denominations in which I have to select 3. 1 for the third card, 1 for the fourth card, 1 for the fifth card. I cannot have any more pairs there, right? So I have to have 3 different denominations. So I have maybe a pair of aces. Now I need to have maybe queens, kings, and 3s. Right? So that is denominations for the third, fourth, and fifth card is combinations, 12 different denominations. I have to select 3 of them for the fourth, fifth, and the sixth card. Okay, this number is 220. You can use your calculator to do that. So this is 220. Okay, you're not done yet. You still have to select, if you selected the third card to be, I don't know, kings, you still need to select one of them, not all 4, right? One of them. So you have to select which king. So you have 4. That's for the third card. For the fourth card, the same thing. You need to select you have denominations, you need to select which of those you need to have. So let's say you have jacks, you need to select which jack you want. Yeah. Jack of diamonds. So you have 4 different options to select jack out of the set of 4. And let's say, what did I say, that you can select 3 for the 5th card, 3s. Which one of the 3? 3 of diamonds, 3 of hearts, 3 of clubs, or 3 of spades. So you have 4 different selections for that. Okay, I just barely squeezed this in. So you have the, again, pair of a kind, 78 different ways. 3 denominations in which you're selecting for a 4th card, 5th card, and 6th card. And then 4 possible ways to get this 3rd card out once you have the denomination. 4 possible ways to get the 4th card once you have the denomination for the 4th card. And the 5th card, the same story. So now, this is 78 times 220 times 4 times 4 times 4. And guess what? That's the same number. Let's do that. So we have 78 times 220 times 4 times 4 times 4, and we get again 1,098,240. Same answer. This is a kind of difficult problem, but it's really not that difficult. Now, if you are drawing a hand of 5 cards, what is the probability that you're actually going to get a pair of 160? While the number of 5 card hands where there is a pair of a kind is 1,240,000. Each 5 card hand is equally likely as any other 5 card hands. You can think about it, but that's the case. And you have a finite number of them. Okay, so we can use that for probability, that you have to divide the number of all of the options that you have for the 5 card hands with 1 pair of a kind with the total number of all of the possible 5 card hands. And if you do that, you get a probability of getting 1 pair of a kind in a random dealing of 5 cards. So I'm going to divide that. So it's 2, 5, 9, 8, 960. So the previous number, 1,098,240 divided with the total number of 5 card hands, 2,598,960, and I get about 42%. 42% is the probability of getting in a random dealing of 5 cards 1 pair of a kind. You can experiment with them yourself. Deal yourself 5 card hand at random many times, and you'll find out that 42% of the time you will really get 1 pair of a kind. So it's very often hand. I think it's about the same probability you're not going to get anything whatsoever. Okay? So this is the most often choice, the most often thing that happen in poker. You get 1 pair of a kind. If it's a pair of aces, that's pretty good pair, but you know, you get anything else. And there's also very often you get nothing at all. It's just 5 cards and you cannot combine them in any way. So what usually people do, I'm going to go for the second. I need a few more cards. I'm going to keep the ace, I guess, if I have an ace. Okay? Now, what is the chance? How many different 5 card hands there are when you have a 4 of a kind? It's a different problem here. Okay. Again, you're going to use the multiplication principle. The first is going to be to get the 4 of a kind. And then you need a 5th card. Okay? It's again multiplication principle. To get 4 of a kind, well, that's an easy one. You have 13 different denominations you can have 4 of a kind. So you just need to select which denomination you have for 4 of a kind. It could be spades, aces. So you have 4 aces. So you have a 13 option, aces or queens or kings or something else. Okay, the 5th card, what is left? 48 8 cards. That's it. That's all there is to it. So this is a very easy problem, very easy to answer. You have 624 different 5-card hands with 4 of a kind. This is very rare to get, so I can tell you that out of 2,598,960 different 5-card hands, only 624 are 4 of a kind. So the probability that at a random dealing of 5 cards you're going to have a 4 of a kind is very small. I'm dividing 624 with 2,598,960, and I'm finding out on my calculator there's some strange number here. That's a scientific notation. This -4 means that I have to move the floating point 4 places there. So it's going to be 0.0002, 4 and on. Approximately 2.5% of a 1%. Or, you know, if you go for the nearest percent, it's approximately 0 chance that you're gonna see in a random dealing of 5 cards, 4 of a kind, right? Unlike in the movies in which you see that all the time. Okay. Now, what is my chance to get 1 pair of a kind, assume blah blah blah. I think I already calculated that before, so this is the answer on probability. In the B part of the problem was the question about in how many ways I can get 1 pair of a kind. So we answered that number is 1,098,240. Here I'm asking for probability of that to happen. Well, I just divide 1,980,240 with 2,598,960, which is total number of 5-card hands, and you get about 42%, which we already answered. And again, what is my chance to get a 4 of a kind? And again, that's the number of 4 of a kind 5-card hands, 624. If you divide it with the total number of 5-card hands, that's approximately 0 chance. It's actually 2.4% of a 1%. It's a very small chance. The number that I get out of my calculator is this one. So my calculator writes scientific notation, but if you write that in decimal notation, that would be, I need to move the floating point 4 places, so I need to move that in front of 2 and then 3 more zeros. Yeah. And there are some more digits here, like a 4, and there are a few other digits to write for 0096038. So 2400960384. I'm reading my calculator. So I need to move the floating point 4 places. I get 3 zeros, 3 decimals with zeros, and then 2400960384. Okay, 3 zeros, 3 decimals, very small number. So this is where the percentages are, and this is where the percentages of percentages are. And then you go on a percentage of a percentage of a percentage. So, which is in this particular case is 2.4% of 1%, approximately 0. Right? Okay, what's my chance to get a full house? Well, I need to first answer how many ways I can get a full house. Okay, how many 5-card hands there are when you will have a full house? What's a full house? 3 of a kind or 2 of a kind? Okay, that's easy problem, sort of. First of all, I need to have 3 of a kind. Then I need to have 2 of a kind. Okay, so I got 3 of a kind. How I got 3 of a kind? I can get a denomination first, which is 13 possibilities, 13 options. Could be aces, could be queens, could be kings, could be tens, could be jacks, could be threes, whatever, but 3 of a kind. Can be out of any of the denomination. There are 13 available. Now, once you select denomination, like for example kings, you still need to select 3 kings out of a set of 4, right? To get the 3 of a kind. And that's going to be 4 chooses 3 combinations. Why combinations? Because the order doesn't matter in which you're gonna, you got 3 kings, doesn't matter in which order you're gonna get 3 kings. King of spade, king of diamond, king of hearts, or king of hearts, king of diamond, king of spades. It's the same story. Okay, so now you have a 3 of a kind. You also need to have a 2 of a kind. Now once you select denomination for 3 of a kind, you cannot have that denomination again, because now you are done with that. So the 2 of a kind had to be something else, right? You can't have 5 aces. So 2 of a kind had to be something else. So you have 12 choices for denomination. And then you have, once you select the denomination, it might be jacks. You need 2 jacks out of a set of 4. And that would be 4 chooses true combinations. Okay? So this is the number of ways to get 2 of a kind. So you have a 3 of a kind and 2 of a kind. The number of ways to get 3 of a kind is 13 times, this number is 4. You can use your calculator, but you can also think in how many ways you can get 3 kings out of a set of 4. Well, the first choice is when you toss out the king of spades. The second choice when you toss out the king of hearts. The third choice when you toss out the king of clubs. And the fourth choice when you toss out the king of diamonds. 4. So this is 4 times 13, and that number is 52. I'm not mistaken. This number here we already met before, I think. This is 6. 6 times 12 is 72. Okay? It's 52 times 72. Now you can multiply, it's not too bad. 52 times 72, 3,744. Okay? So the probability of getting a full house in random dealing of 5 cards is 3,744 divided with 2,598,960. It's approximately 14% of 1%. It's less than 1% chance. This is approximately 1 out of 600. 1 out of 600. If you're dealing a 5-card hands, 600 times, maybe you'll see 1 with a full house. It's very rare, but it's still 6 times better chance than to get a 4 of a kind, because 4 of a kind is 624, and full houses there are 3,744, 6 times more. Okay? I think it's 6 times, right? I can check this out. If I do 44 with 6, what do I get? 624. All right, so full house is 6 times more often than 4 of a kind. Interesting thing to know. Now you know why 4 of a kind is stronger hand than a full house, because much more often, 6 times more often, you're gonna get full house. Both of them are very rare, and both of them usually winning hands. Okay, how about 2 pairs? Okay. By the way, there's another way to calculate this. I'm going to leave that to you to think about it, but this is pretty good enough. I don't need anything else. Okay. What is my chance to get 2 pairs? Okay. And the answer here is about 5%. Okay, so how do I get to that? How do I get this 123,552? That must be the number of ways to get 2 pairs. Okay, So let me think about it. I can do this. First I need two denominations. One for the first pair, one for the second pair. Okay? And then I need to get a pair from the first denomination, pair from the second denomination, and finally I also need to have the fifth card. Okay? So that's the way to think. So I have, in how many ways I can get two pairs? Two denominations. Well, pair from the first denomination, pair from the second denomination, and the fifth card. That's a multiplication principle, and I'm gonna have to multiply all of that. Okay? So, two denominations out of the set of 13 denominations. So it's either queens and kings, or it's aces and threes, or something else. Does the order matter? No. Aces and queens is the same as queen as the aces. If I'm having a two pairs, it's not gonna make any difference in terms of order. Now in a full house it matters. Three of a kind and two of a kind is not the same as two of a kind, three of a kind and two of a kind if you're choosing aces and queens, or three of a kind aces, or if you're choosing three of a kind queens. The order makes a difference there. But now it doesn't. Two denominations out of the set of 13. Okay? So that is, then you have to choose two. You can't have aces and aces. That will not be two of a kind and two of a kind. It will be four of a kind. So it can be aces and queens, right? So it's no repetition. 13 combinations, chooses two. This is just for the denomination. So you're only choosing here, let's say, queens and threes. Okay? Now once you select that, you still need to find out in how many ways you can get the if you have a queens for the first pair, how many ways you can get the two queens out of the set of four, because you have four queens. That is gonna be combinations when the four queens, let's say, chooses two. That's the first pair. And the same story for the second pair. Second pair, you're also gonna have, like, if there are threes, you still need to select two out of four of them, right? It's kind of sound confusing. If there are jacks, it's easier. So you have four jacks, you have to select two. Four chooses two combinations. Order won't matter, but you can't repeat. You can't have jack of spade and jack of spade, right? So now you have two pairs. You still need to have the fifth card, and the fifth card is going to be one of the remaining 44 cards, because you have two denominations selected out. So those are 8 cards that you can't have anymore. You can't, if the fifth card is any one of the cards from the denominations you already selected, you will have actually full house. You will have, you know, 3 of a kind and 2 of a kind. So you need to have 44 different options for the fifth card. Okay, now it's easy to work this out. 13 chooses 2. Oh, okay. I think this is 78. You can check that with your calculator, and I will in a moment. This one is easy. We already had that, so that's 6. And this one is also 6. And the last one, of course, is 44. Okay? And that's exactly this number, 123,552. Now you can check this out. So we have 78. Now you can check this out. So we have time 6 times 6 times 44. 123,552. Okay? So chance of you getting 2 pairs is the number of all 5 card hands divided with total number of 5 card hands, which is 2,598,116. That's about 5%. About 5%. Not very often you're gonna see two pairs. 5% is 1 out of 20, right? Okay, so I said, how do you calculate this 13 chooses two combinations? Again, you write 13 probability combinations chooses 2. Or you can use a formula. My calculator says 78, so that is indeed 78. Now, there's another way to do that. By using permutations. Okay? What would be the story? So there is another way to do that. Okay, you can say it this way. I'm going to select the denomination for the first pair. Then I'm going to select the first pair. 4 chooses 2. Out of that denomination, so there's let's say, I have 13 denominations. Okay, kings, and then 2 kings out of a set of 4. Then I have the second pair. 12 left. 12 denominations left. So let's say, I don't know, jacks. And then you still have to select 2 jacks out of a set of 4. And then you need a 5th card, which is one of the 44 remaining cards. Okay, you have to be careful here, because in this story, you're gonna have, let's say, pair of aces, ace of diamonds, ace of hearts, and you have a jack of spades and jack of clubs. But you're also gonna have jack of clubs and jack of spades, and ace of hearts and ace of diamonds, because this is how it's going to happen. You can have that pair here, you can have that pair here, and the other pair could be here or here. So you actually have twice many more options here. So you really need to divide all of that with 2. So permutation is kind of, this is a little more confusing. The previous way was an easier. Okay? Now when you multiply this, all of this, now this number is 6, this number is 6, so you don't really need any special option or calculus. You have 13 times 6 times 12 times 6 times 44, and then you divide with 2. Again, you're going to get this number. Okay? Check me out. You do that yourself. Right? Here is another card trick. Right? Another card problem. I shouldn't say card trick, because I'm not really doing tricks here. These are not tricks. I'm not doing illusion here. This is all very rational. Okay? If you are selecting 2 cards at random, what is the chance that both of those cards are going to be spades? Okay? There are 2 different ways to do that. One way would be by using counting. Another way would be by using Kolmogorov probability properties. So now we have 2 different ways we can use. Let's use counting. In the deck of 52 cards, you have 13 spades. When you are selecting 2 cards out of the deck of 52 cards, you can get anything. It doesn't have to be 2 spades. It could be, ace of hearts and queen of diamonds, which is not going to be any spade, all right? So, but you can select 52 cards to select from, 2 to select. 1,326 different ways. This is a Newton binomial notation for the combination, right? The same thing. 52 chooses 2 combinations. There is no any fraction on our line. This is not a fraction. This is just a Newton. Sir Isaac Newton was using this to write the combinations, right? So we have 1,326 different ways to get 2 cards out of the deck of 52. Much less than when you have 5 cards, right? When we have 2 millions, blah, 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 whatever. Okay, this is much less, but still lots of different ways. So this is basically what I'm talking about is a 2-card hand. There are 1,326 different two-card hands. Okay? Now, if you want to only have spades, then you have only 13 to choose from, because you have two cards out of the set of 13. There are only 13 spades. So, two-card hands made out of only spades is 13 chooses 2. And again, we are talking about combinations here. And this number is 78. Okay, you can use your calculator. Actually, you already did that. 78. So there are 78 different 5-card hands when there are 2 spades in it. Out of 1,326 different 2-card hands out of the deck of 52. Right? So you have 1,326 different 2-card hands. 78 of those are with 2 spades. Okay, so now you have your probability. 78 divided with, if you divide 78 and 1326, you get approximately 6%, or we should say, you know, you can cancel. The bottom is divisible by 78, so you can actually cancel this. So if you divide 1326 with 78, you actually get 17. See? So I can cancel 78 on the top, 78 on the bottom, I get 1 out of 17. Approximately 6%. So in a random drawing of 2 cards, there's approximately 6% chance that you're going to have 2 spades. It'll be the same if I have 2 diamonds. So there's about, you know, 6% chance that 2 cards are going to be 2 diamonds. What is the chance that it's going to be 2 of the same suit? Like 2 diamonds, or 2 spades, or 2 clubs, or 2 hearts? About 6% for each, so that'd be about 24%. Suit. And 76% is not going to be from the same suit. All right? So that thinking, I'm going to leave that to you. Okay, but I want to calculate this same probability by using properties of probability. The properties of probability I'm going to use here is the property number 6 that says if you are talking about the 2 cards that you're drawing out of this deck of 52 cards, and both of them are spades, that means that you have first card drawn spade and second card drawn spade. Okay, so this is probability of A and B, when A is the first card spade and B is second card spade. We know that the property of 6 of probability, you can calculate this by multiplying the probability of A times the probability of A given B. Oh, excuse me, probability of B given A, right? So this is probability of A, event A, first spade, time probability of B given A. That's how we write conditional probability. That's the property number 6 of probability, right? That's how we get probability of A and B. So this is like A and B. That's what the property of probability says. Okay? What's the chance you're going to have a first spade? Well, you know what? There are 13 spades out of 52, so the chance is 13 out of 52. Which you can also say 1 out of 4, because the spades are 1 out of 4 chance to get a spade, right? To get 4 different suits. Or 13 cards out of 52. Now, that's the first probability. The conditional probability, second spade, once you have a first spade. Well, if you have a first card drawn to be spade, what you are left with is 51 cards. And 12 of them are spades, because 1 card is out and that is a spade. So you don't have any more 13 spades, you have 12 spades in a deck of 51 cards because one card is out already. So that's 12 out of 51. And guess what? This is also 1 out of 17. You can cancel, let's say 13 and 52, so it'll be 1 out of 4, right? If you cancel this and this, you can divide both of them with 13, and now you can divide 4 with 4, you get 1. You can divide 12 with 4, you get 3. So lots of cancellation. And then you can also divide this one with 3, and you get 1, and you can divide this one with 3, and you get 17 when you divide 51 with 3. So basically, after all the reduction, I have 1 out of 17. No surprise, because we already answered them using counting. So using probability properties 1 out of 17, which is about 6%, and using the counting, you get the same conclusion. It's 1 out of 17, you see? There are two different ways to calculate that, okay? So those are all the card tricks I have in this set of problems, okay?